This is a stochastic processes, module 7, Brownian motion and its applications. Lecture 2, processes derived from Brownian motion. In the lecture 1, we have discussed the definition and properties of Brownian motion. We started with the random walk, then the sample path of a random walk. Then we have given few properties of random walk. Followed by that, we have made the derivation of a Brownian motion through the random walk. Then we have discussed the sample path of a Brownian motion. Followed by that, we have discussed few important properties such as sticks and stationary increment, independent increment property, nowhere differentiable property, self-similar property, Markov property, between Gaussian process and the Brownian motion. Also, we have discussed the Kolmogorov equation, and we have given the connection with the heat equation. Then we have discussed the joint distribution of linear process also, and finally we have discussed the martingale property of Brownian motion. So with that, the lecture 1 of module 7 was completed. In the lecture 2, we are going to cover the definition of a geometric Brownian motion. Then a few properties also going to be discussed. Followed by that, we are going to discuss the applications of a geometric Brownian motion, and also few examples of a geometric Brownian motion. Finally, the process derived from Brownian motion, that's a Levy process, also going to be discussed. The definition of a geometric Brownian motion. A stochastic process xt is said to be a stochastic process x of t, where t is varies from 0 to infinity, is said to be geometric Brownian motion if x of t is of the form x naught exponential of wt, where wt is a Brownian motion. That means that whenever you have a Brownian motion, then if you make another stochastic process as a function of Brownian motion, but is of the form x of t is equal to x of 0 e power wt, then the x of t stochastic process is said to be a geometric Brownian motion. You know the range of wt, that is minus infinity to infinity. Since x of t is of the form x of 0 e power wt, therefore the range of xt will be 0 to infinity. The range of xt is 0 to infinity. Therefore, you can use this as a model for the stock price at any time t, and like that you can go for modeling any pricing of any security or derivatives at time t. So the xt can be directly used in the application of finance. We can see the sample path over the time. The xt here, the range is from 0 to infinity, so you can see the continuous functions. You know that the sample path of wt is a continuous function, and the xt, that is a geometric Brownian motion, this is also a continuous function because this is of the form x naught times e power w of t. Now we are going to discuss the very important property, that is the Markov property of geometric Brownian motion. The geometric Brownian motion is of the form x of t is equal to x naught e power wt. Therefore, for any h greater than 0, you can write x of t plus h is same as x naught e power w of t plus h. I am going to verify the Markov property. Therefore, what I am going to do, I am going to add wt and subtract wt in the exponential term. Therefore, the next step will be x naught e power wt plus w of t minus h minus wt. Already we know that x of t is equal to x naught e power wt. Therefore, x naught e power wt can be replaced by x of t. Hence, x of t plus 1 is same as x of t multiplied by e power wt plus h minus wt. That means the stochastic process at the time point t plus h is same as at the time point t multiplied by exponential of the increment between the time points t to t plus h in w. We already know that the Brownian motion or Wiener process satisfies the Markov property, and also the increments are independent along with increments are stationary. Here we are going to use independent, increments are independent. That means since the Brownian motion has independent increments, given xt, the future x of t plus h only depends on the future increments of the Brownian motion. Given xt, the x of t plus 1 t plus h, it depends only on w of t plus h minus w of t. But since w is a Brownian motion, the Brownian motion increments are independent. Therefore, w of t plus h minus wt is independent of 0 to wt. So this feature is independent of the past information. Here the past information is from 0 to small time t. Hence, the Markov property is satisfied because the future depends only on the present, not the past. Therefore, the Markov property is satisfied. Hence, the xt is the Markov process. So this is the above result is valid for all h greater than 0. Therefore, the Markov property is satisfied in the sense the future depends only on the present, not on the past, or it is independent of the past information. Hence, the Markov property is satisfied by xt. Hence, the xt is a Markov process. So, the Brownian motion is also a Markov process. Geometric Brownian motion is a Markov process. Also, geometric Brownian motion is also a Markov process. We are going to find out what is the first and second order moment of geometric Brownian motion. We can use the moment generating function concept. So here, the moment generating function of a normal distribution random variable x with the mean mu and the variance sigma square is given by, for any random variable which is normally distributed with the mean mu and variance sigma square, the moment generating function, it is m x of s, it's a function of s, that is nothing but a expectation of e power s times x. So this expectation is exists because the random variable x is normally distributed. So the moment generating function exists because the moments of all order is exist. So that is same as you can do it separately, this calculation. So here I am just using the result of moment generating function of normal distribution. So that is same as exponential of, so it's a function of s, therefore it is mu times s plus of sigma square s square, where s can take the value from minus infinity to infinity. Why we are using the moment generating function? Because here the geometric Brownian motion and the Brownian motion is connected in the form of x of t is equal to x of 0 e power wt, where wt is normally distributed with the mean 0 and the variance t. Hence, I am using the moment generating function of x of t as a function of s, that is a expectation of e power s times xt. That is same as since wt is normally distributed, with the mu times t sigma square t. For a standard normal distribution, the mu is 0 and the variance is 1. So here we can make out that is same as exponential of mu t s plus of sigma square t s square. By replacing, by using the above logic, you can get is of this form. So here there is a mistake. It is moment generating function of wt and e of s times wt, because x is normally distributed. Here it should not be xt, it should be wt. Here also it is wt. Therefore, moment generating function of wt is same as expectation of e power s times wt. Therefore, this result. Now, using s equal to 1 and 2, now we are finding the mean and variance of geometric Brownian motion, because the mean of xt is x naught times the moment generating function of x of t at 1. So we are using the moment generating function, therefore we can get the mean of the geometric Brownian motion. Similarly, finding the second order moment, you can get the variance of geometric Brownian motion. After simplification, that means first we have to use what is a moment generating function of wt, and we have to use the form xt is equal to x naught e power wt. Using that, you can get the, and after doing some simplification, we will get mean and variance of geometric Brownian motion, that is expectation of xt is x naught times e power mu plus sigma square by 2 times t. And first we can get the expectation of second order moment about the origin, then the variance is equal to expectation of x square t minus expectation of x whole square. Then you can get the variance of xt. So the variance of xt is of the form x naught whole square e power 2 mu plus sigma square t multiplied by e power sigma square t minus 1. By substituting mu plus sigma square by 2 as a r cap or r bar, we will get a expectation of x of t is equal to x naught times e power r cap t. More generally, you can go for expectation of xt divided x of s, that is same as e power r bar t minus s. So in this way, we are finding mean and variance of geometric Brownian motion using the moment generating function of a normal distributed random variable.